Good morning, everyone. Today I'm going to present on the topic Bloom filter for big data query optimization. In today's world, data is growing at an enormous scale. Applications like social media, e-commerce, and banking systems, and the cloud platform generates a huge amount of data every second. Searching through such massive data quickly and efficiently is a major challenge. So, uh, this is where the Bloom filter plays an important role. So in this presentation, I'll explain what a Bloom filter is and how it works internally and why it is useful in big data systems and how company uses it in technologies like Cassandra and HBase. So now let's move to the first slide and I'll just uh, what is Bloom filter? A Bloom filter is an space-efficient probabilistic data structure invented by Burton Harvard Bloom in 1970. And its main purpose is to test whether an element is in a member of set or not. For example, imagine you want to check whether a particular user ID or the product ID or such a keyword exists in huge database or not. A Bloom filter can answer quickly that question without searching the entire dataset. See, the main philosophy behind Bloom filter is trade a small and controllable probability of error of massive savings in memory and input and output performances. Basically, there are two important properties of Bloom filter. The first is zero false negatives. If Bloom filter says no, then the element is definitely not present. If the possible false positive. If it says yes, the element might be present or it might not. So Bloom filter are fast and more memory efficient, but not 100% accurate in positive cases. Now let's move to the next slide and the internal mechanics. And now let's understand how Bloom filter works internally. A Bloom filter mainly consists of two components. The first is bit array. This is simply an array of m bits, and initially all bits are set to 0. So, for example, there are eight bits of which are represented by all zeros like 0, 0, 0, 0, 0, 0. And the second function would be the hash function, where we use k-independent hash functions. Each hash function maps the input element to one possible in the bit array. So if I insert an element, each hash function will generate an index, and those positions will be marked as one. So this space complexity is or big O of m, which means the memory usage depends only on the bit array size, not the size of stored element. And next comes to the standard operations. There are mainly three operations. The first is insertion. To insert an element x, apply k function, get k positions, set those positions to 1. For example, if Apple maps to position 257 and then those positions are set to those bits to the 1. And the second is member test to check whether an element y exists or not. Apply again the same k function. Now check those positions. If any bit is 0, definitely not present. If any bit is 1, might be present. If where the false positive can occur. This is where the false positive can occur. And the next is a deletion. The standard Bloom filters do not support deletion because it if we reset a bit to 0, then the bit might also belongs to some other element. So deleting one item may accidentally remove another item's evidence. So now let's come to the probability of false positives. And now the major limitation in false positive probability, also called as FPP. This is depends on three factors. One is m, the size of bit array, and the n, the number of inserted elements, and the k, the number of hash functions. As more elements are inserted, more bits becomes one. So changes in the chances increase that all checked bits are already one even for an absent element. So minimize false positives the optimal number of hash functions is. Now here the function is k equal to m by n ln 2. This formula helps us balance memory and more accuracy. Now let's go to the next slide. This is the scale problem in big data. Basically, now let's understand why Bloom filters are important in big data systems. In systems like Apache Cassandra and the Apache HBase, the data is stored across thousands of immutable files or segments. For example, SS tables in Cassandra and these store files in HBase. Without Bloom filter, every query would need to check the index of every file on disk. This causes huge I/O bottlenecks, which slow down performance. Disk access is much slower than memory access. So unnecessary disk reads waste time and the reduce the throughput. So now let's come to the next slide, the optimization strategies, where Bloom filter solves this using a technique called segment pruning. The workflow is the step one, the query arrives like for example, where ID equal to X. The step two, the system checks the in-memory Bloom filter. And the step three, if Bloom filter says negative, the system skips the entire disk segment. If the Bloom filter says positive, then only the actual disk IO happens. This simple optimization can reduce disk seeks by over 90% of point queries on high cardinality columns. As a result, we get the faster query response, a lower latency, higher throughput. And now let's go to the next slide. The implementation Apache Cassandra. I don't know what happened to this image is not coming. Let's continue. Now let's see how Cassandra uses Bloom filter. Cassandra creates one Bloom filter per SS table. These filters are stored in memories or the memory mapped files. The Cassandra is wide column stored. A single partition data may be spread across multiple files because because of updates and deletions in LSM tree structure. So where the Bloom filter helps quickly identify which file might not require data. User can tune the parameters called Bloom filter FP change. This controls the false positive rate per table. And now let's come to the next slide. Implementation in Apache HBase. Similarly, HBase also uses Bloom filter. It uses them for store file pruning. HBase checks whether a store file contains a specific row or specific row column combination. There are two types. First is row Bloom filter, filters by row key only, and the row column Bloom filter filters by row plus column qualifier. This provides more granular filter. During compaction, new Bloom filters are generated, so they remain optimized accordingly to the latest data distribution. And coming to the next slide, the trade-off and tuning. Now, accuracy is not free. There is always a trade-off between memory consumption, performance, and accuracy. If we use larger bit array, better accuracy, but more memory. More as function, fewer false positive initially, but slower computation. Smaller bit array, less memory, but more false positives. So tuning Bloom filter depends on application requirements. And now let's come to the advanced Bloom filter variants. There are some advanced versions counting Bloom filter instead of bits. It uses counters. This supports deletion by decrementing values. Scalable Bloom filter, it dynamically grows by adding new filters as more elements are inserted. This prevents false positive probability from increasing too much. And third is Cuckoo filter, a modern alternative. It supports deletion and often performs better for small data sets. To conclude, Bloom filters are a cornerstone of modern big data structure. They provide a smart balance between memory efficiency and speed and the scalability. By identifying whether a data is definitely absent, Bloom filter reduces unnecessary disk access and improves query performance dramatically. This is why they are widely used in systems like Cassandra, HBase, database and caching systems, and distributed storage platforms. So we can say Bloom filter acts as a bridge between massive scale and the low latency performance. Thank you.